Another application we have here in Chapter 6 is work. So, work is a numerical quantity attempting to describe how much, suppose, effort has been expended, and it is calculated by force times distance. So when a force is applied over a certain distance, then that is how much work has been done. So the standard units for work are Newton meters, or if you're using freedom units, foot-pounds. But Newton meters also has a different label, which is joules. So we're going to try to stick to metric, and typically Newton meters is abbreviated NM, and joules is abbreviated with a J, capital. So physics has taken care of the simple problems. If I have a weight and I want to lift that weight up a certain distance, then I'm working against gravity, so the amount of work has been done to lift a 1 kilogram weight up by 1 meter is I'm going to have 1 joule. So the amount of work done in moving a 1 kilogram up 1 meter is going to be force times distance, which is, but force is mass times acceleration, so I'll have 1 kilogram multiplied by acceleration due to gravity, 9.8. And this is multiplied by the distance I have applied the force, which is, again, 1 meter, giving me 1 Newton meter, or 1 joule, for this very simple example. But calculus is made to deal with situations where things are changing. So, for example, if I wanted to lift a rope of a certain weight, as I lift the rope, the amount of rope which is hanging down, or the weight that I'm lifting up, is decreasing. So we'll suppose that a 10-meter rope is currently hanging off the side of a tall building, and it's being coiled up on the top of this tall building. Now, if the density, length density, I suppose, of the rope is 1/2 of a kilogram per meter, we want to find the total amount of work done in lifting and coiling the rope completely on top of the building. So the way this works is actually the way all of the word problems in calculus work. I'm going to chop up the rope. Because if I chop up the rope, I'm going to have a little chunk of rope here of length delta x, and this little length is going to have a mass to it. Specifically, the mass of a chunk of rope is going to be 1/2 kilograms per meter multiplied by delta x meters. So that's the total mass of a little slice of my problem. If I multiply it by gravity, I'm going to have a weight, or a force, and okay, how far do I have to lift this chunk? Well, the distance I have cut the chunk is x, and I have to lift it up by x. So the distance this chunk travels is x. So the work done in lifting just a chunk of this rope well, that's going to be 9.8 times x divided by 2 multiplied by delta x. That's my mass times gravity, which is a force, multiplied by the distance traveled. So the total work done in coiling up this rope, if I lift it all up, then I can think of it as that's the same thing as taking each part of the rope and lifting up each of those parts one by one. Because even if you just focus on one part of the rope and ignore the rest of the rope as it's being coiled up, that one part is going to move up to the top all by itself. And what we're going to do is just add up all the chunks. Chunk is spelled with an N. So this is the sum from I equals 1 up to however many chunks I make of 9.8x over 2 times delta x. But we're used to seeing this type of thing. I could translate this into an integral by applying a limit as n goes to infinity. If I have infinitely many chunks, then I have chunks which are very small, and I'll have a better estimation of the total work done, or specifically the exact work done. I'll have an integral across my x values. Well, what are my x values at which I have chunks of rope available? Well, that's from 0 up to 10. So I'll be integrating from 0 to 10, and I'll be calculating the work for each chunk as far as it needs to travel. But if I perform this integral, this is just going to be, that turns into the integral from 0 to 10 of 4.9 times x dx, which is 4.9 x squared over 2 from 0 to 10, leaving me with a nice 490 divided by 2, or 245. But I should have units on this, right? Well, when I calculated each of my parts, what did I have? I had mass times acceleration. So I had a force in newtons, which was in kilograms times meters per second squared. And then I've multiplied that by a distance, meters. So this is in joules, or newton meters. And a lot of these work problems work by this same slicing principle. If I wanted to, say, calculate the amount of work done in emptying a tank of water, now I want to find the amount of work done in emptying a cylindrical tank, radius 1 meter and height 3 meters, of water out of a spout half of a meter above the top of the tank. So I'll draw a picture so I know what the heck's going on. I have a height of 3 meters. I have a radius of 1 meter. And coming up half a meter out of the top is the spout. And the water is going to be coming out of that way. So what we're worried about is, I guess, picking up all this water and sliding it out of the top. So let's consider I always start my x's at the top, so 0 down to x here. Let's consider a layer of water within the tank. So based on what I've drawn here, x is the depth of the layer. Not the height, but the depth. You can do it in terms of the height, but it's a little bit more difficult. So a layer of water of thickness delta x, that's going to have a volume of pi r squared times delta x. Well, r is just 1, so I can say pi times 1 squared times delta x, so pi times delta x. So how much mass does this water take up? Well, it turns out there are 1,000 kilograms of water per cubic meter. And what I have here is exactly cubic meters. So a layer of water has mass 1,000 times pi times delta x, and that is kilograms per meter cubed times meters cubed, so this is just kilograms. And so it has a weight of 9.8 times 1,000 times pi delta x. And how far does this layer of water have to travel? Well, this layer of water has to travel up to the top of the tank, but then it also has to travel to the top of the spout. So the layer of water must travel x plus 1/2 meters. So the work done in lifting this layer of water is the distance multiplied by the force. Well, I'll go ahead and call this 9,800, multiply those two together, times pi times delta x. And I want to add all of this up. So for all layers, this is going to be the sum of x plus 1/2 times 9,800 times pi times delta x. Or if I translate that back to an integral, I'll have the integral of x plus 1/2 times 9,800 times pi dx. But what are my bounds? Where do my layers of water exist? My layers of water exist when x is equal to 0 all the way down to when x is equal to 3. So I'm going to have bounds here for each layer of water from 0 to 3. And I perform this integral and I'll get the total amount of work done. So if I simplify, I can take these constants out. So this is 9,800 pi times the integral from 0 to 3 of x plus 1/2. We typically get some very nice, easy integrals out of this. If I want some more difficult motion, I suppose we might have a more complicated function, but we'll try not to think about that this time around. And this layering thing works for most applications. Say I wanted to build a building. Well, I'll just have to calculate the weight of each layer of the building and how high up I have to move it. I guess it won't be so much of a building as a pile of dirt, but that's about as far as I got in Minecraft anyway. Now, there's another type of problem we have out of the work section, and that deals with springs, because we have an easy function to describing the force of pulling or pushing springs, and this moves according to Hooke's law. Hooke's law says that the force required to maintain a spring past its equilibrium point is proportional to the distance at which it is pulled or pushed. So the model we have for that is that the force to maintain a spring in a position is equal to K times X. And here K is the spring constant, which is determined by the type of spring you have. And X is the distance past equilibrium. Now, I'm going to talk about things in terms of stretching only. So stretching will be a positive action for me, and compression will be a negative action for me. So if I move the spring in a positive direction, that'll be stretching, and if I move the spring in a negative direction, that will be compression. Now, this slicing works a little bit different than it would for the lifting problems. So let's suppose I have a spring. I'm not going to try very hard with the spring drawings, but we'll say this distance right here is its equilibrium. That is the resting position of the spring. If I had a spring and I just toss it up and it landed on the table, however it sits is its equilibrium. And if I stretch it, I'm going to have a force required to maintain this position. If I were to stretch it a little bit less, I would have a force required to maintain that position. If I were to stretch it a little bit less, I would have a force required to maintain that position. So the way this works is to determine the work done in stretching out a spring, I'm going to look at applying a little bit of force and seeing how far the spring moves. So I'll suppose that I have a spring that has an equilibrium length of 10 centimeters. That's its natural resting length. And I have a spring constant of 20. I want to find the work done in stretching the spring from equilibrium to a length of 15 centimeters. So the way I'm going to do that is going to start here at 10 centimeters. I'm going to apply a little bit extra force, and it's going to stretch by delta x. I'm going to apply a little bit extra force, and it's going to stretch by delta x again. And I'm going to keep doing that until I get to 15. So basically what I'm doing is I'm going to apply f of x amount of force, and the spring is going to move up to that point. And then I'm going to apply f of a little bit more x of force, and the spring is going to move up to that point. So what this looks like is I have the sum I equals 1 up to n. I cut up my interval from 10 centimeters to 15 centimeters into a bunch of little pieces, and I apply the appropriate amount of force for each of those x values, for each of those little pieces. So that's a f of x sub I. Now the work done for each of those little pieces is going to be the amount of force I've applied for that location and the distance it has traveled from the previous location. So that's going to be that force multiplied by delta x. Now in terms of an integral, this means I have the integral of k times x dx every time. Now the k is easy because I told you what it was for this problem. So this is the integral of 20 times x dx. But now the question is, well, what are my bounds? Do I go from 10 to 15? Well, no, I don't. Because this applies k times x, where x is the distance past equilibrium. So what I have to do is I have to subtract the equilibrium length from all of my positions, I suppose. So instead of going from 10 to 15, I will go from 0 to 5, because my spring will be stretched from 0 centimeters past equilibrium all the way up to 5 centimeters past equilibrium. And those are the values that I want to be able to calculate the force. And these are fairly easy integrals. I can do this. This is just 10x squared. That's evaluated from 0 to 5. And that's going to give me 250 somethings. It's actually not joules, because joules are newtons times meters. But what did I calculate here? I calculated newtons, that's taken care of by the spring constant, times centimeters, because this 5 is 5 centimeters past equilibrium. So probably what we actually have here is newtons centimeters. Or maybe centijoules? I don't know. So what we should do is we should calculate this in terms of meters so that we get the right thing. Maybe it's not even newton centimeters because the meters entry is squared in the calculation. We'll try not to think about it too much. Because to get joules, we should translate everything to be in terms of meters, because joules are newtons times meters. So we'll get the integral from 0 to, that was 5 centimeters, so this is 0.05 meters, times 20x dx. And the integral is the same, but it does change our numbers. And it changes our numbers enough that we have to be careful of it so that we don't, accidentally blow up a car or something. So I'll use fractions because I like fractions, and I get 5 over 100, or it looks like I got 250 divided by 10,000. Certainly not newton centimeters, but this will be in joules. If I take a small spring and I stretch it by a little bit, I probably won't get full units. So if you find yourself doing the WebAssign and it seems like you're doing everything right, but it keeps telling you have the wrong answer, check the units of the problem, because it's always good to be mindful of the units to make sure that you are getting what you're expecting to get.